Continue with section 5.4. We haven't actually finished it yet. What I'm doing right now is density and molar mass. This will not appear on a test. You will be given the formula for density versus molar mass. Trying to derive the equation would be extra credit. So if you don't want to worry about this, just skip this section and wait until I move on to gas stoichiometry. That you will have to know. So this part right here, you don't need to watch. But here we go. We're going to derive the relationship between density and molar mass. We have an equation. Density is mass over volume. We have another equation. Molar mass is grams per mole, which would be mass over moles. Remember, N is moles. And then we also have PV equals nRT. Somehow we need to figure out how to use these equations, move them around, to bring this equation and this equation into PV equals nRT. Well, if we look at this, we see density has volume in it. Molar mass has moles in it. So I'm going to isolate for the variables that are in both of these equations and also in the ideal gas law. So solving for volume, we get volume is mass over density. And this one solving for moles, we get moles equals mass over molar mass. Now I'm going to just substitute the equation for volume and the equation for moles into the ideal gas law. So volume will go here, moles will go here, and I get P times M over D. Notice I substituted M over D for volume. And I will substitute M over molar mass for moles, RT. Notice the M's cancel, and now I have an equation that relates density and molar mass. We get P over D is RT over molar mass, and the more familiar version of this equation is molar mass, I'm just moving things around, equals dRT over P. Molar mass is dirt over P. And some students like to think of that as P is dirty, so it's dirt over P. It's kind of silly. Okay, gas stoichiometry we'll do next, and you do need to know that. So this first part was just deriving the relationship between molar mass and density for a gas. All right, so here's a gas stoichiometry problem. Before we get into the problem, let me just back up. So gas stoichiometry is really just combining stoichiometry we've already learned with the ideal gas law. So in this case, all of a sudden there's information about temperature, pressure, and when you see, and we're asked about a volume. When you see volume, temperature, pressure, you should be thinking about PV equals nRT. So there's your thought process. So we can just set up, what do we know about this problem? Let's look. We've got temperature is 80 degrees Celsius. We always have to have Kelvin. So that is going to be 353 Kelvin. Pressure is 823 millimeters of mercury. And we're going to have to convert that to atmospheres, because we always have to convert to atmospheres if we're going to use the ideal gas law. Notice we would not be using a two-state problem here because things are not mentioned. The pressure, the temperature, everything is not mentioned twice. And that is 1.08 atmospheres. What else? We're trying to find the volume. So we have PV equals nRT, and I've got P, I've got V, I've got T, I know R. Well, I don't have V. V is what we're trying to find, sorry. I still need moles, but we have to be careful. We need to find moles of N2. Moles of N2, because the question is asking about how many moles of, what volume of nitrogen gas. Let's look back here. Notice nitrogen is N2. So moles of N2, we got to figure that out. Well, we're going to use stoichiometry. We figure this out, stoichiometry, because the other piece we have, I want to make sure I spell this right, stoichiometry. The other information we have is that there's 60.0 grams of NaN3. Well, our reaction, whenever you're given a reaction, you should assume you're going to have to use it. So don't just use the grams of sodium azide. Sorry, that's called sodium azide right here. Don't assume that I can just use the moles of sodium azide in my PV equals nRT, because I'm asked for volume of nitrogen. And notice sodium azide is a solid. So I'm going to convert the sodium azide to moles of nitrogen. Moles of nitrogen. So we first do grams of sodium azide to moles of sodium azide using what? That's right, we use molar mass. And our molar mass is 65.02 grams of sodium azide to 1 mole of sodium azide. And to go moles to moles, we always use the reaction coefficient. So we have 2 sodium azide to 3 nitrogens. 2 moles sodium azide to 1 mole of nitrogen. Now, nitrogen, you have to make sure that you notice it was N2, not N. And that gives us 1.38 moles of nitrogen. Now we've got everything we need. Moles of nitrogen. This is going to be 1.38 moles of N2. I've got everything except for volume, and now I can just plug into PV equals nRT. We will isolate V. V is nRT over P. We plug in all of our data. Now you could pause this. I'm going to pause and just solve it out. And I plugged everything in, did the math, solved it. We get 36.9 liters. We're going to do one more problem, and after it's written out, if you want to pause and see if you can do this on your own, see if you get the right answer on the answer sheet that has everything, you're good. All right, here's our problem, and I'm going to do this one a little bit differently. Notice on most of these problems I've been putting all of the information down the left side. This time I'm going to put all the information around underneath each chemical that it refers to in the reaction. So let's see. We want to find the mass of NH3. So we'll go to NH3 and we'll put question mark grams, because that's what we are looking for. And how much of that can be made from 2.5 liters of hydrogen? So now the liters over here are with the hydrogen, 2.5 liters. Oh, and this hydrogen is at 25 degrees Celsius, and it's at 125 kilopascals. So that's all the information I'm given. And I look at this and I say, okay, over here on the hydrogen, I'm going to have to use PV equals nRT. I've got a volume, I've got a temperature, I need to convert that to kelvins, and I've got a pressure, which I'm going to need to convert to atmospheres. This is 1.23 atmospheres. I just divided by 101.3 kilopascals doing that conversion. Okay, so I know from all of this information here, I could find my moles of H2. Now if I can find my moles of H2, I've got pressure, volume, temperature, so I can solve for moles. If I have moles of H2, can I get over to grams of NH3? Sure, beautiful stoichiometry. So let's solve this problem. First we'll get our N of H2. N is PV over RT. Now I'm going to plug this all in. I'm going to pause, put everything up on the board. Okay, so I calculated that all out, hopefully correctly, and I got 0.126 moles of H2. Note that I should only actually keep 2 sig figs because of this 2.5 liters right there. I'm going to keep 3 for now to do the next calculation, and then I have to remember to round my final answer to 2 sig figs. It is okay with me if you were to round here, but it's best to keep a few extra, 1 or 2 extra sig figs, usually 1 is enough, until you get to the very end. But let's see, we are at H2, we're at the hydrogen now, and we're trying to get to grams of NH3. So we have our 0.126 moles of H2. So we have to convert moles of one chemical to moles of another chemical. We're trying to get H2 over to NH3. What do I use? The coefficients. 3 moles H2 to 2 moles NH3. And I asked for grams. I asked for mass. You have to know mass means grams. It's very important. So let's see. 1 mole of NH3 is 17.04 grams of NH3. And that is, all right, that is 1.43 grams of NH3. But I can only keep 2 sig figs, so we get 1.4 grams of NH3. Okay, second problem done. Okay, 5.5 is Dalton's law of partial pressure. And here's a visual picture of Dalton's law. Dalton's law basically says if you have a mixture of gases, the total pressure of all the gases is the combined pressure, it's called partial pressures, of all the gases in the mixture. So if I have 2 gases and I combine them together, so now we have the same volume, same temperature, we put those together into one container, the total pressure is P1 and P2. If I had 3 gases, it would be P1 plus P2 plus P3. So we just keep adding all the gases together, and that gives us our total pressure. These are the pressures of gas 1 and gas 2. We call these pressures, when we have a mixture, we call the pressure of each component of the mixture a partial pressure. And that does not mean a fraction. It is a fraction of the total pressure, or it's a part of the total pressure, but don't think of it as you're making a fraction. It's still the pressure of the gas. And we would still calculate, we can still use the ideal gas law to calculate PV equals nRT, where N1 is the moles of gas 1 and P1 is the moles of gas 2. Notice we were saying that V and T are constant. So P total would equal the total moles times RT, and P2 times volume would be the total moles of gas 2 times RT. Okay, we can rearrange this equation, and ultimately we can get that P of gas 1 over P total will equal the moles of gas 1 over N total. And this particular ratio has a special name and a special symbol. It's called mole fraction. Mole fraction. You have to know mole fraction. So mole fraction is the moles of a gas over the total moles, which is equivalent to the pressure, partial pressure of a gas over the total pressure. Let's do some problems. Okay, here's our problem. We have a gas mixture. It contains nitrogen and oxygen. The total pressure is 1.30 atmospheres. The partial pressure of N2, notice I read this as the partial pressure of N2, is 0.500 atmospheres. Find the partial pressure of oxygen and the mole fraction of both species. All right, we know that P total, this should be very easy, is PN2 plus PO2 because those are the gases in the mixture. So let's see, 1.30 atmospheres is equal to, what was N2 is 0.500 atmospheres plus PO2. So my partial pressure of oxygen is going to be 1.30 minus 0.500 atmospheres. And this is 0.80 atmospheres is the partial pressure of oxygen. Note, I did not keep 3 sig figs, even though both numbers in the original problem had 3 sig figs. So I had 3 here and 3 here. However, when we're doing addition subtraction, we have to keep the answer to the least precise last significant figure placeholder. So this is to the hundredths, this is to the thousandths. I can only keep my answer to the hundredths. All right, I still have to calculate my mole fraction. So mole fraction of oxygen would be my partial pressure of O2 over the total pressure. There's my partial pressure of O2. I just calculated it, 0.80 over 1.30. And that comes out to 0.62. And my my mole fraction of my N2 will be my partial pressure of N2 over the total pressure. And that is 0.500 over 1.30. And that is 0.385. Mole fraction has no units because the pressure units, the atmospheres, cancel out. So whenever we talk about mole fraction, that is a fraction, and you don't write the answer in fractional form. You have to calculate a decimal number, really important. Notice I kept 3 sig figs here because I'm doing division now, and I can keep 3 sig figs. One other thing is when we add up our mole fractions, they should add up to 1, so you can always do a check. When we add up the fraction of everything, it should add up to 1, so 0.62 plus 0.385. It's going to add up to a little bit more than 1 because of sig figs, but it's close enough. We're good. All right, end of that problem. Okay, so Dalton's law, the reason we actually really care about Dalton's law is because sometimes we collect gases over water. And when we do that, the collected gas has the gas pressure plus the pressure of water vapor. Water, we don't think of there being water in here in this gas space, but there is. There's a little bit of water vapor. And you look up the water vapor pressure in tables. Oh, sorry, I didn't realize I was still recording. So this water vapor pressure, we looked that up in tables, and this vapor pressure of water depends on temperature. We'll actually be doing a lab where we're going to collect a gas over water, and the key is that the total pressure in the collected gas here is going to equal the gas pressure plus the water vapor pressure. So the important piece is that the gas pressure is the total minus the water vapor, and P total, this is another important thing. We have air pressure pushing down on this water, and if we get the height of the gas equal to the height of where the water is in the container, then the P total in the collected gas will equal the outside air pressure, P air outside. So we get an equation that the gas pressure is equal to the air pressure minus the water vapor pressure. And we just have to remember to use that equation whenever we collect a gas over water. Okay, and the last thing we will go over in this video is section 5.6, the kinetic molecular theory. KMT. Whenever you hear KMT, we're talking about the kinetic molecular theory. And this theory has 2 very important things. First, it says that kinetic energy, KE is kinetic energy, is just a constant times temperature. So at the same temperature, all gases have the same, oops, sorry, computer's doing something, have the same average kinetic energy. Doesn't matter if you're nitrogen, hydrogen, oxygen. If you have 2 gases at the same temperature, they have the same exact average kinetic energy. This is really important. You have to know this. Okay. All right, we have, your book shows 4 postulates. I combined postulates 2 and 3 into one postulate. So we only have 3 postulates shown here. So 3 important things about the kinetic molecular theory. These are the kinetic molecular theory postulates. First, gas is composed of particles separated from each other by distances much greater than their size. Basically, this is saying that the particles have no volume. The particles themselves have no volume compared to the volume of the container. So the gases are obviously in a container that has volume, but the particles moving around in that container, the particles themselves have no volume. Second postulate is gas particles are in constant motion and the collisions are elastic. So when particles collide, it's like billiard balls, like pool table balls. They collide, they bounce off of each other. And there are no attractive or repulsive forces. So when those particles collide, there's no force acting between the particles. That's an important assumption. Last thing, I already talked about this, I'm emphasizing it. The average kinetic energy is a constant times temperature. And you probably haven't had any physics yet, but kinetic energy is 1/2 mv squared. And in this case, we're talking about the mean square speed. There's an equation for this in your book. You don't need to worry about it. You just need to know the average kinetic energy is 1/2 mass times the average velocity, the mean square speed. All right. This leads to an equation for effusion. Effusion is when you have a gas in a container and you get a little pin-sized hole and the gas molecules can start exiting through that hole. Balloons are like this. There happen to be more than one hole in a balloon, but over time a balloon will get flatter because of effusion. Some of the molecules in the balloon are getting out. Some of those gas particles are getting out. And there's an equation for how fast a gas will effuse. And we derive that equation from the kinetic energy at the same temperature. The kinetic energy is constant times temperature, the average kinetic energy. So we will look at this equation right here and notice we can cancel the halves. And I'm going to rearrange this to obtain that V1 squared over V2 squared is equal to m2 over m1. I'm going to take the square root over both sides. So the square root of the average root mean square speed velocity, square root of both sides of gas 1 is equal to the square root of the mean squared velocity for gas 2. That's equal to, oops, I'm doing the square root, oh yeah. No, I'm not. So I'm going to take the square root of the right side. Now, this left side over right side, we can talk about the rate of effusion. That would be the velocity, the mean square velocity is directly proportional to the rate at which something would escape. So we convert this equation into the rate of a gas 1 would escape to the ratio of the rate at which gas 2 would escape is equal to the molar mass of gas 2 over the molar mass of gas 1. And this is a very important equation that you must know. Okay, so let's do a quick, no, I think we're going to be done for now. Okay, we'll do some of this in class. Okay, we are going to do one problem, and I will write it out right now. Okay, here's our problem. A gas at a certain temperature effuses at a rate 0.25 times the rate of O2 at the same temperature. What is the molar mass of the gas? So we know we have an equation. Rate of O2 over the rate of the gas is the square root of the molar mass of the gas over the molar mass of oxygen. I also know that the gas effuses, this gas effuses, so R of the gas effuses at a rate 0.25 times the rate of O2. Is 0.25 times R of O2. So you have to be careful when you're reading these to see if you've got another equality in here. So rate of the gas is 0.25 times the rate of O2. I'm going to just substitute this into my equation. I also know that the molar mass of oxygen is 32. So I'm going to substitute our gas into the equation. So I have RO2 over 0.25 times RO2. I just substituted in the R gas value is the square root of the molar mass of the gas over 32. So the rate of the gas cancels. I have 1 over 0.25 is the square root of the molar mass of the gas over 32. I'm going to square both sides. And also I'm going to solve this 1 over 0.25. That is actually equal to 4. So I have 4 squared is the molar mass of the gas over 32. The molar mass of the gas is 32 times 16, which is 512 grams per mole. Let's check our sig figs. Let's see. Oh, I had 2 sig figs in the problem, so I can really only keep this 510 grams per mole. And I am done. Okay, that's it.